Hi, this is Mrs. LaBarbara. Today's topic is describing motion with VT graphs part 2 area. The objectives for today is know the meaning of the area on a VT graph, understand the relationship between the area and the displacement, be able to describe motion with a given shape of VT graph, determine the area on a VT graph, and relate the shapes of DT graph, VT graph, and AT graph. The meaning of the area on a VT graph. For a velocity versus time graph, the area bound by the line and axis represents the displacement. Recall that average speed equals d over t, so from this equation we can derive d equals v times t. This, whenever you see the two multiply together, this kind of indicated area. Remember the length times width, that's the area. Let's just review how to calculate areas of different shapes. So basically, we have three shapes here. The area of rectangle is base times height. In this case, or base can be velocity, this would be your base, this would be height, or this can be your base or that can be your height, it doesn't matter. So the two multiply together give you the displacement. Now sometimes in velocity versus time graph, your area can be a triangle. Remember how to find the area of the triangle? That's 1/2 base times height. It doesn't really matter which one you use as base, which one you use as height. Last one is sometimes we have to calculate area of a trapezoid. Some of you probably remember the equation for the area of a trapezoid. For those of you who doesn't remember, this is 1/2 base times height 1 plus height 2. So what is base? Take a look at trapezoid. The special trapezoid, we have the two sides that are parallel to each other. Those two sides parallel to each other, we call those height 1 and height 2. The lines in between that's perpendicular to the two sides, we call that base. So it's 1/2 base times the height 1 plus height 2. Or some of you probably prefer, you can just, in order to find this trapezoid, you can use the big area, big triangle, minus the little triangle. Or some of you probably wants to find the area of this triangle plus this rectangle. So whichever way you want to do, you feel comfortable with, that's okay. Let's do some examples. So this is to determine the displacement of the object during the time interval from 2 to 3 seconds. And the first 2 seconds for practice B. So let's see, the first one is a trapezoid. So what is the base? Base is the one that's perpendicular to the two lines. These two lines parallel to each other, those are the height. Height 1 or height 2 or vice versa, doesn't really matter. So that's the equation I used. If you can use something else, oh, this one's supposed to be 1. So 1/2 base, height 1 plus height 2. Base in this case from 2 to 3 seconds, that's just 1 second. This interval is 1 second. Height 1, I used 20, height 2 is 30, so I have d equals 25 meters. If you use different ways, you can use the big triangle minus little triangle, that's fine. You should have the same answer. Here is another one for B. For this trapezoid, again, this is the base, and height 1 and height 2. So base is 2 seconds from 0 to 2. Height 1, I just use from the right, from the left, then to the right, 30 plus 10. You can use big triangle, right, minus little triangle, or you can use the triangle on the top plus the rectangle on the bottom. Whichever way you feel comfortable to do, that's the way you're supposed to do it. Take a look at this one. The graph represented the velocity of an object traveling in a straight line as a function of time. Determine the magnitude of the total displacement of the object at the end of the first 6 seconds. Again, the displacement in velocity versus time graph is the area, only up to 6. So you need to find the area of this trapezoid. Again, these are the two that's parallel to each other. So we use that height 1 and height 2. And this would be your base. So base times height 1 plus height 2. The base is 10. So from 0 to 10 and height 1. I just use this top as height 1. That's 4 seconds. Height 2 is 6 seconds. So the total area is 50 meters. Again, you can use your own way. You can use the triangles or whatever you want to do. Triangle plus rectangle. Here is another example. So this one is what is the magnitude of displacement of the car from t equals to 1 second to equals to 3 seconds. Again, in velocity versus time graph, this area is the displacement. So this area is again a trapezoid. So what is the base? Base is the line that's connected to parallel lines. So here is the base, which is 2 seconds. Here is height 1, which is 10 meters, and here is height 2, 30 meters per second. So height 1 is 10 meters per second. So again, the base is 2 seconds, height 1 is 10 meters per second, height 2 is 30 meters per second. So your total displacement should be 40 meters. Now let's take a look at the next example. The graph represents the linear motion of a car. Again, what graph is it? Velocity versus time graph. So during which interval does the car has largest displacement? In velocity versus time graph, what represents displacement? Area. So which area is biggest from A to B, B to C, D to E, or E to F? So the answer is obvious to me. The area under DE is the largest. So that's the biggest displacement. What is the acceleration of the car at t equals to 6 seconds? So at t equals to 6 seconds, what is acceleration? Acceleration is the slope of the graph. Looks like acceleration is constant between 5 to 7 seconds. Acceleration is constant negative because slope is negative. How do we find the slope? Change of y divided by change of x. So this is y2, 0 minus y1, 20 divided by x2, 7 minus x1, 5. So you should have negative 10 meters per second squared. Negative, that makes sense because the slope is negative. Next question, what is the average velocity of the car during interval DE? Well, during interval DE is right over here, so it's constant. So it's just 20 meters per second. Now, DT, VT, AT graphs, they are all motion graphs. They can represent the same motion, okay? So let's see how do we graph those for constant velocity. So in DT graph, remember the slope is the velocity. So for constant velocity in displacement versus time graph, the slope has to be constant. Now in the VT graph, the slope is acceleration. Don't confuse this, okay? Motion can be described by both graphs, as a matter of fact, by all three graphs. For example, let's try to do an object that's moving with positive constant velocity. If velocity is positive constant, that means in displacement versus time slope is positive constant. So the graph should look like this. In velocity versus time graph, constant positive would look like something like that. That's a constant positive above 0. The line straight constant. In both cases, acceleration equals 0. How do we graph 0 acceleration? Look like that. Okay, so again, all three graphs represent the same motion. DT-VT graph for accelerated motion. So we can also represent accelerated motion. So graphs DT, VT, and AT actually for an object moving with constant positive acceleration. Let's see, if acceleration is positive, that means velocity has to increase, right? Velocity has to be positive increase. That means your slope has to be positive increase. What kind of shape gives you increasing positive slope? So slope should look like this. Why is slope is positive increasing? Because slope is velocity. Now in velocity versus time graph, velocity is the acceleration. What about acceleration? Acceleration is positive. So the slope has to be positive. So slope is acceleration. So slope is constant positive. Would look like this. Acceleration is constant positive. That means acceleration looks like this. Horizontal line above zero. Okay, so again, all graphs represent same motion. Let's do a couple of examples. Which pair of graphs represent the same motion of the object? Take a look at example A. Slope is the velocity. So slope is constant, positive. So velocity should be constant, positive. But in this case, velocity is negative because it's below zero. So it's not A. Take a look at B. Slope is velocity. Slope is constant, negative. This one says velocity is changing. First it's decreasing, then it's increasing. So it's not this. Slope is velocity. What can we say about this slope? Slope is positive increasing. What is velocity saying? Positive increasing. So the answer is C. Take a look at this. What can we say about this slope? Slope is positive, but it's decreasing, becomes zero over here. Then it becomes negative and increasing. But this one says velocity is constant, so it's not that. Another example, which pair of graphs represent the same motion? Take a look at this one. Slope, negative constant. That means velocity is negative constant. No, velocity is positive increasing. Slope is positive constant. Velocity is positive constant. Oh, velocity is constant positive. So the answer is B, all the others are wrong. Which pair of graphs represent the same motion? Slope is positive, but it's decreasing. That means velocity, or in this case, it's distance and time. That means speed is greater than smaller. Speed is constant. No, not the same motion. Speed is increasing because slope is increasing. Oh, speed is increasing. That's the one. Okay, that's the answer. Looks like it is at rest. Speed should be zero. No, speed is not zero. Speed is increasing. Looks like speed is negative. By the way, this can never happen. Speed can never be negative. Speed is the magnitude. Speed is always positive. You never on a highway say speed limit is negative 55 miles per hour, right? So this cannot happen. This is invalid diagram. So that's it for today. Thanks for watching. See you next time.